We tend to keep our greatest mysteries at a safe distance, the inside of a black hole, the edge of the universe, the first instant of time, places no one can ever go. But the largest unsolved mystery in all of science is not far away at all. It is in the room with you. About 85% of the matter in the universe is invisible, a substance that holds every galaxy together and yet has never been seen, touched, or identified. Right now, as you lie here, billions of its particles are passing through the walls, through the bed, through your own body, and on through the whole of the Earth, without leaving a single trace. We can map exactly where it sits across the entire cosmos. We can weigh it to 2 decimal places, and we have no idea what it is. Settle in and turn the lights down. If this is your first time here, hit subscribe, because by the end of this, the most ordinary darkness around you will feel like the greatest unanswered question there is. Now, let's ease our way slowly into the dark. Part 1. The 5%. Everything you have ever seen is the exception, not the rule. Take a moment to sit with what that sentence is actually claiming. Every star you have ever noticed on a clear night, every photograph ever returned by a telescope, every galaxy smeared across a long exposure, every planet, every moon, every drifting grain of dust between worlds, and every atom in your own 2 hands, all of it, added together, makes up only about 5% of what the universe is really made of. The other 95% is something else entirely. And the larger share of that something else, the part we are going to settle into tonight, is a substance that gives off no light, reflects no light, and absorbs no light. It has never been held in a hand, never sealed in a jar, never seen by any instrument anyone has ever built. We call it dark matter. The name is almost a small joke, because it is not dark the way a shadow or a lump of coal is dark. It is clear. Light passes straight through it as though it were not there at all. Picture the night sky the way you usually do, and then change just one thing about the picture. Take all of that light every star, the soft spilled band of the Milky Way, the faint smudges of other galaxies, and imagine it as a thin froth of foam riding on the surface of an ocean you cannot see. The foam is bright. The foam is the part that catches your eye. But the foam is not the ocean. It is only a skin on the top of something far larger and entirely unlit, and it is the ocean underneath, not the foam, that decides where the bright parts are allowed to gather. Tonight we are going to talk about the ocean. The history of science keeps teaching us one lesson, and it keeps having to repeat the lesson because we keep forgetting it. We once placed the Earth at the center of creation, and we were wrong. The Earth is one planet circling an ordinary star. We then assumed the Sun was special, and we were wrong again. It is one star among several 100 billion in this single galaxy. We assumed our galaxy was the whole of existence, and we were wrong a third time. It is one galaxy among roughly 2 trillion. Each correction moved us a little further from the center and made our place look a little smaller against the whole. The discovery of dark matter is the next turn of that same screw, and in some ways it is the most humbling turn of all, because it does not merely move us off the center. It tells us we are not even made of the main material. We are built from a minority substance, living on the outskirts of one galaxy, on a planet circling an unremarkable star, and the stuff of our bodies is outnumbered about 5 to 1 by something we have never seen. Let me try to turn that 5 to 1 ratio into something you can actually hold in your hands. Imagine you could gather every scrap of ordinary matter in some region of space, all the stars, all the glowing gas, all the cold dust, all the planets, and pack it into a single pile and weigh it. Then imagine weighing the dark matter sitting in that same region. The dark pile would come out about 5 times heavier, not 5% heavier, 5 times. For every truckload of matter you can see, there are roughly 5 truckloads of something invisible occupying the same space, announcing itself only through gravity. And it is not stacked neatly off to one side, where you could turn and look at it. It is spread through and around everything at once, overlapping the stars and the gas and the empty gaps between them, threaded through the whole structure of the cosmos the way water soaks through a sponge. You are not looking at the dark matter from the outside. You are standing in the middle of it. What keeps this from being merely bleak, what makes it almost gentle once you sit with it, is that the invisible majority is not working against us. It is the reason there is anything here at all, anything to demote, anyone to do the demoting. We will come back to that, because it is the turning point of the whole story. For now, just hold the shape of the claim, because everything tonight is built on it. The bright universe is the small part. The thing it floats in is the large part. And the large part is a mystery we have not solved. For most of human history, nobody suspected the ocean was there. The sky looked complete. You looked up, you saw points of light, and it was reasonable to assume that the light was the universe, and the universe was the light. What else would it be? We are creatures built around our eyes. We trust what we can see, and we quietly assume that what we cannot see is simply empty. That assumption feels like common sense. It is also, as it turns out, almost entirely wrong. And the strange thing is that we now know this with more certainty than we know almost anything else in science. We can measure the unseen part. We can map it. We can tell you how much of it sits inside this galaxy and how much wraps around the next one and how it is spread across the entire reachable universe. We have its weight to 2 decimal places. What we cannot tell you is what it is. That gap is the whole story. It is the reason this is not just another fact about space, but the single most honest mystery in all of physics. In almost every other case, when scientists can measure something this precisely, they understand it. They know what it is made of, what rules it follows, where it came from. With dark matter, the order is reversed. We have the measurement and not the meaning. We are like someone who can describe the exact shape, weight, and movement of a thing in a darkened room, who can tell you it is leaning against the far wall, and that without it the ceiling would collapse, and who still has no idea what the thing actually is. Let me give you the numbers, because they set the scale of everything that follows, and a number on its own tells you nothing until you can feel it. The matter you think of as normal atoms, the stuff of stars and planets and people, accounts for roughly 5% of the total contents of the universe. Dark matter accounts for about 27%. And a third ingredient, dark energy, which is a separate mystery for another night, makes up the remaining 68% or so. Set dark energy aside for now, and look only at the matter, only at the stuff that clumps and pulls and builds. Out of all the matter in existence, the ordinary kind, your kind, is outweighed by the dark kind by about 5 to 1. For every kilogram of the matter you can see and touch, there are roughly 5 kilograms of something you cannot. About 85% of all the matter in the universe is invisible. Now here is why this is not a distant abstraction, not a fact that lives only at the edges of the cosmos. The galaxy you are sitting inside right now, the Milky Way, does not hold itself together with the gravity of its stars. There is not nearly enough visible matter to do the job. The stars near the outer edge of our galaxy are moving so quickly that by every law of motion we trust, they should have been flung off into the blackness between galaxies long ago, the way a child loses their grip on a fast enough merry-go-round. They have not been flung off. Something is holding them, something with a great deal of mass, spread out in an enormous unseen cloud that reaches far past the bright spiral of stars, is gripping this entire galaxy and keeping it whole. Without that invisible grip, there would be no Milky Way. The sun would not have a galaxy to belong to. The night sky would not have a shape. So, you are not an observer standing outside this mystery, looking at it through a telescope. You are inside it. You are standing on a small rock that circles an ordinary star, and that star is held in its place by the gravity of a substance no one has ever identified. The ocean is not far away. You are floating in it. This is the quality of dark matter that I find hardest to shake, and I want to plant it now so it can grow as we go. It is not exotic in the sense of being remote. It is exotic in the sense of being everywhere and unaccounted for. The best current estimates suggest that as you lie there, particles of dark matter are very likely passing through the room, through the walls, through the bed, and through your own body in their billions every second, and continuing straight down through the entire bulk of the earth and out the other side without so much as brushing against a single atom of you. The reason you cannot feel them is the same reason we cannot find them. They almost never touch ordinary matter. Almost. That word almost is where 40 years of the most patient experiments in human history have made their stand, and we will get there. But I am getting ahead of the story, and this story deserves to be told slowly, because it was discovered slowly by people who mostly did not want it to be true. Nobody set out to find an invisible universe. The idea was forced on us, again and again, by measurements that refused to add up, by careful people checking their work and finding the same impossible answer each time. The honest history of dark matter is not a history of a brilliant guess. It is a history of a stubborn discrepancy that would not go away, that grew larger and more undeniable with every decade and every new instrument, until eventually it stopped being an error to explain away and became the largest single thing in the universe. So before we ask what it is, before we go a mile underground into the tanks of liquid xenon where people are still hunting for it tonight, we have to ask a simpler and stranger question. How can anyone possibly be sure that something invisible is real? How do you weigh a thing you cannot see, cannot touch, and cannot catch? The answer begins almost a century ago, with a difficult, brilliant, abrasive man staring at a cluster of galaxies that, by his arithmetic, should not have been able to hold itself together at all, and with a conclusion so far ahead of its time that the rest of physics simply set it aside and forgot about it for 30 years. Part 2. The cluster that should have flown apart. In 1933, an astronomer named Fritz Zwicky did a piece of arithmetic that should have changed the world, and almost nobody listened. Zwicky was working at Caltech, and he was, by every account, a difficult man. He was brilliant, combative, and almost gleefully rude to his colleagues, and he had a habit of being right about enormous things decades before anyone was ready to agree with him. He was among the first to predict that collapsing stars could form what we now call neutron stars. He suggested that the gravity of a galaxy could bend and magnify light, an idea that is now one of our most powerful tools, and which we will come back to. But the work that matters most for tonight is what he did when he turned his attention to a swarm of galaxies called the Coma Cluster. The Coma Cluster is an enormous gathering of galaxies, more than 1,000 of them, all bound together in one region of the sky and all moving under each other's gravity. Zwicky wanted to know how much the cluster weighed, and he had two completely different ways to find out. The first way was to count the light. You look at all the galaxies, you measure how brightly they shine, you make a reasonable estimate of how much matter it takes to produce that much light, and you add it all up. That gives you the mass you can see. The second way was to watch how the galaxies move. In a cluster held together by gravity, there is a balance between two things: how fast the members are moving and how much mass is pulling on them to keep them from escaping. Measure the speeds, and you can work backward to the total mass required to hold the swarm together. If the galaxies are moving slowly, you do not need much mass to keep them bound. If they are moving quickly, you need a great deal. When Zwicky measured the speeds of the galaxies in the Coma Cluster, he found them tearing around at hundreds of kilometers per second. They were moving so fast that the gravity of all the visible matter, every glowing galaxy he could count, fell catastrophically short of what was needed to hold them together. By his calculation, the cluster did not have anywhere near enough mass to keep from flying apart. The galaxies should have scattered into the surrounding space long ago, like a swarm of bees with nothing to hold them in formation. And yet there the cluster was, plainly intact, plainly bound, plainly old. There were only two ways out of that contradiction. Either the laws of gravity and motion that had worked flawlessly for 2.5 centuries were wrong, or there was a great deal of matter in that cluster that no one could see. Zwicky chose the second answer. He proposed that the cluster was filled with a large quantity of unseen mass, holding everything together by its gravity, and he gave it a name in German Dunkel Materie, dark matter. The visible galaxies, the part that shone, were only a small fraction of what was actually there. The rest was dark, silent, and enormous. Here is the part that should stop you. Zwicky's estimate of how much was missing was not a polite 10 or 20%. By his early numbers, the unseen mass outweighed the visible mass by a factor of many hundreds. Now, that specific figure turned out to be too large, and it is worth being honest about why, because this channel does not paper over the messy parts. Zwicky used a value for the expansion rate of the universe that was badly off by the standards we use today, and that error inflated his result. With modern numbers, the coma cluster's missing mass is more like 5 to 10 times the visible matter rather than hundreds of times. But notice what that correction does and does not do. It shrinks the size of the discrepancy. It does not remove it. Even with every later fix applied, the cluster still contains far more mass than anything that shines inside it. The conclusion survived the correction. The unseen matter was real. It is worth slowing down on how simple and how sturdy Zwicky's reasoning actually was, because the same logic runs underneath everything that came later. Picture swinging a stone on the end of a string around and around your head. The faster you swing it, the harder the string has to pull to keep the stone from flying off. If you saw a stone whirling around very fast on the end of a thread that looked far too thin to hold it, you would conclude one of two things. Either the thread is much stronger than it looks, or it is about to snap, and the stone is about to be lost. The galaxies in the coma cluster were the fast stones. Gravity was the string, and the visible matter could only supply a string far too weak to keep those fast galaxies whirling in place. Either the cluster was in the act of flying apart, which made no sense, because clusters like coma are old and settled, or there was a great deal more gravity, and therefore a great deal more mass, than anything that shone. That was the whole argument. It did not require exotic ideas. It required only the courage to trust a measurement that pointed somewhere uncomfortable. And Zwicky, for all that he was overlooked here, had a record of being right about uncomfortable things long before anyone else. Working with the astronomer Walter Bade, he proposed that when a massive star dies in a supernova, it can collapse into an impossibly dense ball of neutrons, the object we now call a neutron star, decades before such things were confirmed. He suggested that the gravity of a massive object could act as a lens, bending and magnifying the light of things behind it, an idea that is now one of the central tools of astronomy and one we will lean on hard tonight. Time proved him right, again and again. Yet his largest claim, of all that most of the matter in the universe might be invisible, was the one the field was least ready to hear, and so it was the one that waited longest for company. There is a lesson in that about how science actually moves. It is not always the weakest ideas that get ignored. Sometimes it is the ones that ask us to give up too much of what we assumed we already understood. And the world shrugged. It is genuinely strange, looking back, how little happened next. Here was a careful measurement, made by a serious scientist, pointing to the possibility that most of the matter in a cluster of galaxies was of an unknown and invisible kind. Today, that would be front-page news for a year. In the 1930s, it mostly sat in the literature, occasionally cited, rarely pursued. Part of the reason was Zwicky himself, whose personality did not invite collaboration. Part of it was that galaxy clusters are complicated, distant, and easy to wave away. Perhaps the measurement was off. Perhaps the cluster was not as settled as it looked. Perhaps there was some gas or faint matter that closed the gap. And part of it, I think, was simply that the idea was too large to swallow. It is one thing to admit you have missed a little. It is another to be told that the part you can see is the minority, and that the universe is mostly made of something you have never met. The human mind resists a correction that big. It is easier to assume the books will balance once someone checks the math more carefully. For about 30 years, that is roughly where the matter stood. A strange result, filed away. An unsettling possibility, not quite believed. The problem with dismissing the coma cluster, though, is that a cluster is a crowd, and crowds are messy, and messy things are easy to explain away. To force the issue, you would need something simpler. You would need to find the same impossible result, not in a chaotic swarm of 1,000 galaxies, but in a single, ordinary, well-behaved galaxy, spinning quietly on its own. You would need to watch one galaxy turn and catch it breaking the same law in plain sight. That is exactly what happened next, and it was carried out by an astronomer who was not trying to overturn anything at all. She had chosen her subject precisely because it seemed safe, uncontroversial, and quiet. She simply wanted to measure how galaxies spin. What she found instead was the clearest evidence anyone had ever seen that most of the universe is missing, and this time it would not be so easy to look away. Part 3. The curve that refused to fall. The astronomer was Vera Rubin, and the instrument that made it possible belonged to her colleague, Kent Ford. In the late 1960s and into the 1970s, Rubin set out to measure something that sounds almost too simple to matter how fast the stars in a spiral galaxy go around. She started with the nearest large spiral to us, the Andromeda Galaxy, and she had a reason for choosing such a plain question. Rubin had run into hostility earlier in her career when she strayed into more contested territory, and galaxy rotation seemed like calm water, a problem nobody would fight her over. Kent Ford had built an extraordinarily sensitive spectrograph, an instrument that could collect the faint light from individual clouds of gas far out toward the edge of a galaxy and measure how that light was shifted by motion. Light from something moving toward you is squeezed slightly bluer. Light from something moving away is stretched slightly redder. By reading those shifts, Rubin and Ford could clock the orbital speed of gas and stars at different distances from a galaxy's center, point by point, all the way out to the faint rim. To understand why their result landed like a thrown stone, you have to remember how orbits are supposed to work, and our own solar system is the perfect teacher. The Sun holds almost all the mass of the solar system at the center, and so the planets obey a clean rule that Kepler and then Newton pinned down centuries ago: the farther out you go, the slower you move. Mercury, close to the Sun, races around at about 48 kilometers per second. Far off Neptune ambles along at only about 5. The drop-off is steep and predictable, because once you are outside most of the mass, gravity weakens, with distance and orbital speeds fall away. A spiral galaxy looks, at first glance, like it should behave the same way. The light is concentrated toward the middle, in that bright central bulge, and it thins out toward the edges. So the stars far out, past most of the glowing material, ought to move slower and slower, just like the outer planets. That is not what Rubin and Ford found. As they measured their way outward from the center of Andromeda, the orbital speeds climbed, and then, instead of falling off the way every expectation demanded, the curve simply refused to fall. The stars and gas at the outer edge were moving just as fast as the ones much closer in. The line on their graph, which should have bent downward toward the rim, ran flat, straight out as far as they could measure. And a flat rotation curve has only one honest interpretation. If the outer stars are moving that fast and are not being thrown off into space, then there must be far more mass out there, pulling on them, than the light reveals. The mass has to keep increasing with distance, long after the stars have thinned to almost nothing. Each spiral galaxy, in other words, had to be sitting inside an enormous unseen reservoir of matter, a roughly spherical cloud reaching far beyond the bright disk, weighing several times more than every visible star combined. Let me put you out there for a moment, because the numbers do not land until you stand inside them. Imagine yourself at the outer edge of a spiral galaxy, drifting with one of those distant stars. Behind you and below you is the whole luminous wheel, the bright crowded center, and the curved arms turning slowly against the black. By every rule your intuition trusts, you should be in the slow lane out here. There is almost nothing visible beyond you. The glowing matter is all behind you, toward the middle, so its pull should be weak this far out, and you should be loafing along, barely keeping up, but you are not. You are moving just as fast as the stars far inside the bright core, carving through the dark at a speed that should long ago have torn you loose and flung you away into the emptiness between galaxies. Nothing you can see is holding you. There is no great mass behind you to account for it. And yet you are held firmly, steadily, by the grip of something enormous and entirely invisible that surrounds you on all sides, something you are moving through right now and cannot detect, a presence known only by the fact that you have not been let go. You reach out in every direction, and your hand closes on nothing. Still you turn and turn, held by the dark. That is the moment dark matter stopped being one strange cluster and became a property of galaxies themselves. There is a regularity hidden in all those flat curves that makes them stranger still, and it is worth knowing about because it will matter later when we weigh the alternatives. When astronomers gathered rotation curves from hundreds of galaxies, large ones, small ones, bright ones, faint ones, they found that the way a galaxy rotates is tied with remarkable tightness to how much ordinary, visible matter it contains. Tell an astronomer how much glowing matter a galaxy holds, and they can predict its rotation with surprising accuracy. That is a clean, simple pattern, and a clean pattern is exactly what you would not naively expect if each galaxy was simply wrapped in its own independent cloud of invisible matter, free to be heavy here and light there. The invisible matter, somehow, seems to know about the visible matter and to arrange itself in proportion. Nobody fully understands why. It is one of those quiet facts that sits politely in the data and undermines easy stories from both sides of the argument. Vera Rubin, for her part, never claimed to have discovered a new substance. She was careful, almost understated, about what she had found. What she would say is that she had measured something real and repeatable. Galaxies do not rotate the way the visible matter says they should, and that the explanation was someone else's to settle. That modesty is part of why the work was so hard to dismiss. There was no grand theory attached to it for skeptics to attack, only a stack of clean measurements that kept saying the same thing. Galaxy after galaxy, the curve refused to fall. And slowly, through the 1970s and into the 1980s, the weight of all those quiet, careful, repeatable measurements did what a single dramatic claim never could. It changed the default assumption of an entire field. The unseen matter went from an oddity at the edge of respectability to something a working astronomer simply expected to find wrapped around every galaxy they studied. Because here is what made Rubin and Ford so much harder to wave away than Zwicky had been. A single cluster of 1,000 galaxies is a crowd, and a crowd can be messy in ways that fool a measurement. But a spiral galaxy turning on its own is about as clean and simple a system as the universe offers. There was no crowd to blame, no chaos to hide behind. And It was not one galaxy. Rubin and Ford, and then others, measured spiral after spiral after spiral, dozens of them, and the curves came back flat every single time. By the year 1980, when Rubin and Ford and a colleague published a sweeping survey of these measurements, the pattern was undeniable. Every spiral galaxy they looked at was embedded in a halo of unseen mass, several times heavier than everything that shone. The exception had become the rule. The ocean was under every patch of foam, not just one. This time, the world did not shrug. The flat rotation curves, arriving on top of Zwicky's old cluster result, were too clean and too repeatable to dismiss, and, through the 1980s, the existence of some large invisible component of the universe moved from a fringe idea to a mainstream expectation. Astronomers began to take seriously that most of the matter in any given galaxy was of a kind nobody had identified. But moving things, as evidence, share a hidden weakness, and a careful skeptic would have spotted it immediately. Both Zwicky's clusters and Rubin's galaxies were arguments built on motion and gravity. In every case, the reasoning was the same things are moving too fast for the visible mass. Therefore, there must be extra mass we cannot see. That logic has a loophole. What if the problem is not missing mass at all? What if our law of gravity, the rule that connects how things move to how much mass is present, is simply wrong out there at the faint edges of galaxies, where the pull is gentle and slow? If gravity behaved a little differently than Newton said, in those conditions, you might explain the fast stars with no invisible matter whatsoever. It is a serious possibility, and we are going to take it seriously later tonight, because it never fully goes away. To close that loophole, you cannot keep watching things move. You need a completely different kind of witness evidence that does not depend on speeds and orbits at all, evidence that comes at the question from a direction gravity tinkering cannot easily follow. And it turns out there is not just one such witness. There are several, gathered with instruments that have nothing to do with one another, looking at the universe in ways Zwicky and Rubin never could. When you line them all up, side by side, they do something that should not be possible for a mistake. They all give the same answer. Part 4. 6 witnesses. The next witness does not watch anything move at all. It watches light bend. One of the strangest and most beautiful predictions to come out of Einstein's work is that mass curves space, and that light, travelling through curved space, follows the curve. A heavy object does not just pull on other matter. It bends the very path that a beam of light takes as it passes by. This was not idle theory. In 1919, astronomers measured the positions of stars near the edge of the sun during a total eclipse and found that the sun's mass had shifted their apparent positions, bending their light by exactly the amount Einstein had predicted. Mass deflects light. The universe agreed. Now scale that idea up from the sun to something enormous, a whole cluster of galaxies, the kind of object Zwicky had studied. A cluster that massive bends the light of anything unlucky enough to lie behind it. The light from distant galaxies, far on the other side, gets caught in the cluster's curved space and warped on its way to us. Sometimes it is smeared into long, thin arcs, as if the background galaxy had been pulled like taffy around the cluster. Sometimes, when the alignment is nearly perfect, the light wraps almost all the way around into a glowing ring. And in the subtler, more common case, the shapes of thousands of background galaxies are all stretched a little in the same direction, a faint, coherent distortion spread across the whole field. We call this gravitational lensing, and it is one of the most powerful tools we have, because it lets us weigh an object using nothing but the bending of light from far behind it. Here is why that matters so much for our mystery. Lensing does not care how fast anything is moving. It does not depend on orbits or speeds or the balance between motion and gravity. It depends only on how much mass is present and where that mass sits, because mass is what bends the light. It is a completely independent way to put the universe on a scale, and it comes at the question from a direction that has nothing to do with Zwicky's swarming galaxies or Rubin's spinning disks. So when astronomers measure how strongly a cluster bends the light behind it, and work out how much mass it must contain to do that, they are running an entirely separate experiment. They are checking the books a different way. The books come back the same. Cluster after cluster bends light far more strongly than the visible matter could ever account for. To produce the lensing we actually see, there has to be several times more mass than every glowing galaxy and every cloud of hot gas combined. The unseen matter is there again, in the same rough proportion, measured by a method that knows nothing about velocity. And lensing does something the earlier methods could not. Because the amount of bending depends on where the mass sits, astronomers can use it to draw maps, actual maps of where the invisible matter lies, sketched out across a cluster or across a patch of sky, like a contour map of hills you cannot see, traced only by the way they warp the light passing over them. Sit with that for a moment, because it is the strange situation at the center of this whole subject, and I want to give it words now so we can carry it the rest of the way. We can map this stuff. We can tell you where it is, in this cluster and that one, in the halo of this galaxy and the next. We can weigh it. We can chart how it is spread across the reachable universe. We know where it is, and we have no idea what it is. That sentence is going to come back tonight, and each time it returns, it should sit a little heavier, because the more precisely we pin down where dark matter sits, the sharper the embarrassment becomes that we cannot say what we are pointing at. And notice what has happened to the skeptic's loophole. Remember the worry from a moment ago that maybe nothing is missing, and gravity itself just works differently at the gentle outer edges of galaxies. That was a reasonable doubt when all our evidence came from watching things move. But lensing is not about motion. It is about mass-bending light. So now any alternative idea has a much harder job. It is not enough to tweak how orbits behave. You would have to explain why light bends, as though enormous unseen mass were present, in the same places, in the same amounts, that the moving galaxies already pointed to. Two completely different methods, motion and light bending, are now pointing at the same invisible thing in the same locations. A mistake in one would not have to agree with a mistake in the other, but they agree. This is the real reason dark matter became impossible to dismiss. It is not one measurement, it is a convergence. We have galaxy clusters held together by more mass than they show. We have spiral galaxies spinning too fast for their visible matter. We have light bending around clusters as though they were far heavier than they look. And we have two more witnesses still to call tonight, each from a completely different branch of astronomy, the faint afterglow of the Big Bang itself, which carries the recipe of the early universe written into it, and the great web of galaxies spread across all of space, whose very existence demands that the invisible matter was there from the beginning. 5 independent lines of evidence, soon 6, gathered by people using different instruments, asking different questions, often unaware of one another's work. And every one of them returns the same answer that most of the matter in the universe is of a kind we cannot see. When 5 completely different roads all lead to the same impossible town, you stop believing that 5 different map makers each made the same mistake. You start believing the town is real. The light-bending witness deserves a little more of your attention because of what it has grown into. In the most dramatic cases, when a distant galaxy sits almost perfectly behind a massive cluster, its light is bent all the way around into a complete glowing circle, a ring of light surrounding the unseen mass. These are called Einstein rings, and they are some of the most beautiful objects in the sky because what you are looking at is the literal shape of bent space, a halo of light tracing the gravity of something you cannot see. But the everyday workhorse of the method is subtler. Across any patch of sky, The gravity of all the intervening matter slightly stretches the shapes of the millions of background galaxies behind it, all in gently aligned directions, like the way a sheet of old window glass distorts the view through it. By measuring that faint, shared distortion across millions of galaxies at once, astronomers can reconstruct where the mass lies that did the bending, and most of that mass is dark. This has turned gravitational lensing from a way of weighing single clusters into a way of mapping the invisible across enormous stretches of the universe. Because galaxies at different distances are bent by different amounts, the technique can even sort the dark matter by depth, building something close to a three-dimensional map, a chart of the unseen scaffolding running through space, layer by layer. We are no longer just inferring that dark matter exists. We are drawing its portrait across the sky, tracing the great invisible web that ordinary galaxies are strung along like beads. And every time we extend that map, it agrees with everything else: the spinning galaxies, the swarming clusters, the recipe in the ancient light. The town is not only real, we are now surveying its streets, even though we still cannot say what its buildings are made of. But the single most convincing piece of evidence is not any one of these careful measurements taken alone. It came from a violent accident out in the universe, two enormous clusters of galaxies that slammed through each other at millions of kilometers per hour. In that wreckage, for one fleeting cosmic moment, the invisible matter was pulled clean away from the ordinary matter and left standing in empty space, far from anything that shines. And when astronomers mapped that collision, they did not just infer the dark matter, they watched it separate and cast its shadow all on its own. Part 5. The Smoking Gun. To understand why this one collision changed the argument, you first have to know what a cluster of galaxies is actually made of, because it is not mostly what you would guess. When you look at a cluster, your eye goes to the galaxies, the bright spirals and ellipticals scattered through it. But the galaxies are not where most of the ordinary matter lives. Most of the normal matter in a cluster, the regular atoms, the protons and neutrons, is not in the galaxies at all. It is in enormous clouds of thin, superheated gas filling the space between them, gas so hot it glows in X-rays. The stars in the galaxies are only a small share of the everyday matter. The hot gas is the bulk of it. And then, surrounding and outweighing all of it several times over, is the dark matter, the invisible component that holds the whole cluster together. So a cluster has three ingredients in rising order of mass: the stars you see, the hot gas you need an X-ray telescope to see, and the dark matter you cannot see at all. Now take two such clusters and let them collide. That is the bullet cluster, the wreckage of two galaxy clusters that crashed through each other, a collision astronomers studied closely in a landmark piece of work published in 2006. And in that collision, the three ingredients behaved in three different ways, and that is the entire point. The galaxies, first, galaxies inside a cluster are tiny compared to the space between them, like a few scattered gnats in a cathedral. So when two clusters collide, the galaxies almost never hit each other. They sail right past, through the gaps, and come out the other side barely disturbed. The hot gas does the opposite. Two enormous clouds of gas cannot pass through each other cleanly. They smash together, they drag, they heat, they pile up, and they slow down, getting stranded in the middle of the collision while the galaxies coast on ahead. So, already, in the aftermath, the ordinary matter has split into two parts, moving differently. The galaxies pulled out ahead, the gas left lagging behind in the center. And the dark matter? If dark matter is real, and if it barely interacts with anything, then it should behave like the galaxies, not like the gas. It should pass straight through the collision, almost untouched, sailing on ahead with the galaxies, leaving the ordinary gas stranded behind. Two great clouds of invisible matter should have glided right through each other and come out the far sides, far away from where most of the normal matter ended up. So astronomers did two measurements. With an X-ray telescope, they mapped the hot gas that showed them where most of the ordinary matter was, piled up and glowing in the middle. And with gravitational lensing, the light-bending trick from a moment ago, they mapped where the total mass was by watching how the wreck warped the light of galaxies far behind it. Then they laid the two maps on top of each other. And here is the result that earned the title of the paper, which called itself, plainly, a direct empirical proof of the existence of dark matter. The mass and the ordinary matter were not in the same place. The bulk of the mass, traced by the bending of light, was not sitting on the hot gas where most of the normal matter was stranded. It had moved on ahead, out to two clumps far from the center, sitting exactly where the dark matter should have sailed to. The gravity was where nothing visible remained. Let me put you above it, drifting over the collision as it plays out across millions of years. Two clusters drift toward each other across an immense gulf, each one a swarm of galaxies wrapped in a glowing cloud of gas and an even larger cloud of unseen mass. They meet. Watch what happens to each part. The galaxies, sparse and small, slip through the gaps between one another and keep going, hardly grazed, coasting out the far sides. The two clouds of hot gas, enormous and unable to pass cleanly, slam together in the middle and snag, heating and slowing and piling into a stranded glowing wreck that lags behind. And the dark matter, the heaviest part, the part you cannot see, pours straight through the collision, as if nothing were there to stop it. Two silent mountains of mass, passing clean through each other and gliding out the far sides with the galaxies, leaving the bright ordinary gas abandoned in the center behind them. Now the light from distant galaxies, crossing through the wreck on its way to your eye, bends, and it bends hardest, not around the glowing gas, where the visible matter sits, but around the two dark clumps out front, where there is nothing to see at all. The heaviest thing in the collision is the thing that left no light behind. You are watching the invisible pull on the universe from a place where, by every appearance, nothing is there. It is worth being careful here, because a result this strong invites obvious objections, and they were all checked. Perhaps, you might say, there is ordinary matter we simply failed to see out where the gravity peaks, some cold gas or faint material doing the pulling. But the hot gas mapped in X-rays is where the great majority of the ordinary matter in such clusters lives, and that gas is stranded in the middle, not out at the gravity peaks. There is nowhere near enough unseen ordinary matter out where the lensing is strongest to account for the pull. Perhaps the lensing map itself is mistaken, but lensing is geometry, the bending of light by mass, one of the best tested predictions we have, and the measurement has been repeated and refined. Every ordinary escape route leads back to the same conclusion. The mass is real, it is where nothing shines, and it passed through the collision untouched, and the bullet cluster did not stay alone for long. Since that first careful study, astronomers have found other colliding cluster systems that show the same telltale separation, the glowing gas snagged and slowed in the middle, the bulk of the gravity carried on ahead with the galaxies and the dark matter. Each new collision is another instance of the same story playing out in a different corner of the sky. The visible matter dragging while the invisible glides through as though the wreck were not there. One collision, taken alone, a determined skeptic might explain away as a quirk of interpretation. Several of them, all telling the identical story, are not a quirk. They are a pattern, and the pattern is the one dark matter predicts. This is why, of all the evidence, the colliding clusters are the result that physicists reach for first when someone asks whether the invisible matter is really there. You can argue with a graph of rotation speeds. It is much harder to argue with a photograph of gravity sitting in empty space. This is why the bullet cluster is called the smoking gun, and why it is so hard for the skeptics to answer. Think back to the loophole, the idea that maybe there is no dark matter, and gravity just works differently than we think. In that picture, gravity comes only from the matter you can see, behaving in some modified way. But if that were true, the gravity in the bullet cluster should be centered on the ordinary matter on the hot gas, where most of the normal mass actually is. Instead, the gravity is centered far away from the gas, out where the invisible matter sailed to, and nothing shines. A theory that says gravity comes only from visible matter has to explain why the gravity is strongest exactly where the visible matter is not. That is a very uncomfortable thing to explain. The simplest reading, by far, is the one the title chose. There is a substance there. It passed through the collision. It does not interact much with anything, and it carries most of the mass. So now we have it from 4 directions that could not be more different: swarming clusters, spinning galaxies, bending light, and a cosmic collision that pulled the invisible matter clean away from the visible and let us watch it stand alone. The existence of dark matter is, at this point, about as secure as anything in science. But notice what none of these has told us yet. They tell us dark matter is here and there and in that galaxy and in this cluster. They do not tell us how much there is in total across the entire universe, as a fraction of everything. For that, you cannot weigh one galaxy or one collision. You have to weigh the whole universe at once. And remarkably, there is a way to do exactly that. Using the oldest light, there is a faint glow left over from the birth of the cosmos that still falls on us from every direction in the sky. Part 6. The Recipe. The oldest light in the universe has been travelling for almost the entire age of the universe, and it is still arriving from every direction right now. It is called the cosmic microwave background, and to understand it, you have to go back to when the universe was very young, about 380,000 years old. Before that moment, the cosmos was too hot for atoms to hold together. It was a glowing fog of bare particles and light, all tangled together, so dense and so hot that light could not travel in a straight line. It bounced endlessly, trapped, the way light is trapped inside the body of the sun. Then the universe expanded and cooled enough for the first atoms to form, and in that instant the fog cleared. Light was suddenly free to travel, and it set out across space, and it has been travelling ever since. That light still washes over us today, stretched and cooled by the expansion of the universe into a faint hum of microwaves, sitting at about 2.5 degrees above absolute zero, falling on the Earth from every part of the sky at once. It is a photograph of the universe as it looked when it was 380,000 years old, and it is the closest thing we will ever have to a baby picture of everything. Let me add one careful detail about how that picture gives up its secret, because it is the cleanest fingerprint of dark matter we have. The ripples in the ancient light come in a series of sizes. Like the notes of a struck bell, there is a loudest note, and then a set of fainter overtones above it. The relative loudness of those overtones is what carries the recipe. And here is the elegant part. The dark matter changes the pattern of overtones in a way ordinary matter cannot fake, because the dark matter was sitting still in its gravity wells, while the ordinary matter rang back and forth under the pressure of light. The presence of all that quiet, unmoving dark mass alters how strongly the second and third overtones sound compared to the first. So when Planck measured the exact loudness of each note in that ancient bell, it was reading the amount of dark matter directly off the sky, not guessing, not inferring from galaxies, but measuring it in the structure of the universe's first light. And there is one more witness, the sixth, and it closes the question of what the dark matter is not. In the first few minutes after the Big Bang, before a single star existed, the whole universe acted as a furnace and forged the lightest elements, most of the hydrogen, almost all the helium, a trace of lithium. The exact proportions of those elements depend with great sensitivity on how much ordinary matter was present in that furnace. We can measure those proportions today in the oldest and most pristine clouds of gas we can find, and they pin the amount of ordinary matter to the same 5% the ancient light reports. Two completely independent windows onto the infant universe, the leftover light and the leftover elements, agree to the decimal place, and both leave the same gap. There is far more gravitating matter than there are atoms to account for it. Whatever fills that gap was not forged in the furnace and does not ring under light. It is something else, and it was there from the very first minutes. That photograph is almost perfectly smooth, but not quite. Across it lie faint ripples, places that are very slightly hotter or colder than average, by about 1 part in 100,000. Those ripples are not flaws. They are the most information-dense pattern in all of cosmology because they are frozen sound. In the hot fog of the early universe, pressure waves were rolling through the glowing plasma like sound waves through air, sloshing the matter back and forth. When the fog cleared and the light broke free, those waves were frozen into the pattern of hot and cold spots we still see. And the characteristic sizes of those spots, how big the ripples are, and how their sizes are distributed, form a kind of fingerprint of exactly what the early universe was made of. Here is the part that matters for our mystery, and it is one of the most elegant things in physics. Ordinary matter and dark matter leave different marks on that fingerprint, because they behaved differently in the early fog. Ordinary matter was tangled up with the light. It felt the pressure of all those trapped photons, so it sloshed back and forth in the sound waves, pushed and pulled by the light it was bound to. Dark matter felt none of that. It is blind to light, so the photon pressure meant nothing to it. While the ordinary matter sloshed, the dark matter simply sat where gravity gathered it, forming quiet wells of mass that did not move with the waves. So the ordinary matter was sloshing in and out of pits that the dark matter was holding still, and that difference shows up directly in the pattern. The relative sizes of the ripples in particular, how tall some of them are compared to the ones beside them, depend on how much ordinary matter there was doing the sloshing and how much dark matter there was holding the wells. Read the heights of those ripples carefully, and the early universe tells you its own recipe. A spacecraft called Planck read that recipe more precisely than it had ever been read before, mapping the ancient light across the entire sky. And the recipe it returned is the one we started with tonight. About 5% of the universe is ordinary matter. About 27% is dark matter. About 68% is dark energy. Within the matter alone, there is roughly 5 times as much dark matter as ordinary matter. The same 5-to-1 ratio that Zwicky stumbled toward in a single cluster, that Rubin found in spinning galaxies, that Lensing found in the bending of light, there it is again, written into the oldest light in existence, measured by a method that has nothing whatsoever to do with galaxies or motion or collisions. Think about how strange and how strong that is. The cosmic microwave background is a snapshot of the universe, as it was 380,000 years after the beginning, long before there were any galaxies at all, long before the Sun, long before the Earth. It knows nothing about Vera Rubin's spirals or Zwicky's cluster. It is a completely separate witness, testifying from the dawn of time, and it gives the same answer as everything that came after. When measurements this independent agree this closely, you are no longer looking at a possible mistake. You are looking at a fact about the universe. Most of the matter is dark, and it has been dark since the beginning. So let the proportion settle on you, slowly, the way it deserves. Everything you have ever known, every person who has ever lived, every ocean, every mountain, every star you can name, every world we have ever dreamed of reaching, all of it is built from the 5%, the ordinary matter, the foam on the surface. We are not the main ingredient of the universe. We are the trace, the rounding error, the thin, bright minority riding on top of something far larger that we are only beginning to understand. There is a particular humility in that, and it is not a sad one. It is the same humility that came when we learned the Earth was not the center, and then that the Sun was just one star among hundreds of billions. Each time, the place we thought was the whole turned out to be a small corner of something greater. This is the next step in that long lesson. The matter we are made of is not the universe's main substance, it is the exception. And the cosmic microwave background carries one more revelation, one that takes dark matter from a curiosity about proportions and turns it into the reason any of us are here at all. Because the dark matter did not simply share the early universe with ordinary matter, sitting quietly off to one side, it went first. Those quiet wells of unseen mass, holding still while the ordinary matter sloshed around them, those wells are where everything began to gather. The dark matter laid down the framework, the unseen scaffolding, into which all the ordinary matter would later fall to build the galaxies, the stars, the planets, and eventually us. Without that invisible head start, the universe as we know it would not have had the time to assemble a single galaxy. To see why, we have to ask what the cosmos would look like if the dark matter had never been there at all. Part 7. The Architect. Imagine running the universe again without dark matter and watching what fails to happen. You start the same way, the hot fog, the expansion, the cooling. In the ordinary matter, there are those faint ripples, the slightly denser patches that the cosmic microwave background reveals, differing from their surroundings by only about 1 part in 100,000. For galaxies to form, those tiny lumps have to grow. Gravity has to pull more matter into the denser spots, making them denser still, until they collapse into clouds, and the clouds into stars, and the stars into galaxies. The trouble is time. The universe is about 13.8 billion years old, and it has been expanding the whole while, pulling matter apart even as gravity tries to draw it together. If you only had ordinary matter to work with, those 1 part in 100,000 ripples are simply too faint. Gravity could not have amplified them fast enough against the expansion to build galaxies in the time available. Run that universe forward and you get a thin, smooth haze of gas, slowly spreading, never quite gathering. No galaxies, no stars, no planets, no one to notice. There is a second problem, and it is worse. Remember that ordinary matter, in the early fog, was bound up with light, pushed around by all those trapped photons. That coupling did not just make it slosh, it actively kept it from clumping. As long as the light and the ordinary matter were tangled together, every time gravity tried to pull the ordinary matter into a lump, the pressure of the light pushed it back out. Ordinary matter could not even begin to gather into the seeds of galaxies until the fog cleared 380,000 years in. It was held smooth by the very light it was bound to. For all that time, dark matter had neither problem. Because it is blind to light, the photons never pushed it around, and it was free to start clumping long before the fog cleared, while the ordinary matter was still held smooth. By the time the light broke free, the dark matter had a head start of hundreds of thousands of years. It had already begun gathering into a web of gravity wells, denser regions strung across the young universe. So when the ordinary matter was finally released, it did not have to start from nothing. It fell into wells that were already there, already dug, already waiting. The gas poured into the dark matter's framework, piled up in the densest spots, and there, in those pre-built pits of invisible mass, it grew dense enough and hot enough to ignite the first stars and assemble the first galaxies. We can test this. We can take everything we know, the ripples in the ancient light, the laws of gravity, the proportions of matter, and we can run the whole thing forward inside a computer, simulating billions of years of cosmic history. When we include cold, dark matter, building its scaffolding first, the simulations grow a universe that looks like ours, with galaxies strung along enormous filaments, gathered at bright nodes, Separated by immense empty voids, a great cobweb of matter spanning all of space, the same structure our telescopes actually map when they survey millions of real galaxies. Take the dark matter out of the simulation, and that structure never forms. The web does not appear. The galaxies do not assemble in time. The universe stays a thinning haze. The only way to grow the cosmos we live in the time we have, is to let the invisible matter go first and build the frame. So slow down here, because this is the moment the whole subject stops being about astronomy and becomes about you. Every galaxy that exists, including this one, formed inside a halo of dark matter. The Milky Way did not gather itself. It condensed inside an enormous invisible well of dark matter that had been waiting, drawing in gas until that gas could light up as stars. Our galaxy is, in the most literal sense, a bright deposit at the bottom of a dark pit we cannot see. And every step that followed the formation of the sun inside that galaxy, the gathering of the leftover material into planets, the settling of one particular rock at one particular distance where water could pool and chemistry could turn into life, and the long climb from that chemistry to a creature that could lie in the dark and wonder about any of it, every step happened on a foundation laid by the invisible matter. You are downstream of it. Your existence traces back, without a single break in the chain, to a head start given to the universe by a substance no human being has ever seen, identified, or held. The atoms in your body are part of the bright 5%. But the reason those atoms ever got to gather into stars, into worlds, into you, is the 95% you cannot perceive at all. You owe your existence to a stranger you will never meet. I want to make those simulations concrete because they are some of the most ambitious calculations human beings have ever performed, and they are the strongest test we have of this whole picture. Researchers take a virtual cube of universe, fill it with the faint ripples the ancient light reveals, pour in cold, dark matter, according to the recipe, and then let gravity run for the equivalent of more than 13 billion years, tracking how every region pulls on every other. What grows inside the cube is a structure they call the cosmic web galaxies gathered into glowing knots. Those knots, strung along enormous bridges of matter, hundreds of millions of light years long, and between the bridges, immense and nearly empty rooms of darkness. Then the astronomers point real telescopes at the real sky, map where millions of actual galaxies sit, and compare. The simulated web and the real web match the same knots, the same bridges, the same empty rooms. Then they run the cube again with the dark matter removed, and the web simply never appears. The ordinary matter, left to itself, never gathers in time. The galaxies do not form. The cube stays a fading haze. Our universe is only possible in the version with the invisible scaffolding switched on. Stay with the weight of that for one more moment, because it is the still point at the center of the whole night. You are not only made of the bright 5%. You are a late, fragile, improbable consequence of a head start. The universe was handed by something that has never once shown you its face. Every ancestor you have ever had, the whole unbroken line of living things, stretching back to the first cell in some warm pocket of the early Earth, lived and died inside a galaxy that exists only because the invisible matter went first and dug the well it formed in. The stranger did not just build the scenery around your life. It built the stage your entire lineage has stood on, and it is still here, still holding that stage together, while remaining the single largest thing in science that we cannot name. I find that I cannot make that thought small. We are used to owing our existence to things we can point to: the sun, the earth, our parents, the long line of living things before us. This is different. This is owing your existence to something that has no face, no glow, no surface, something that is, even now, the largest unanswered question in physics. The framework that made you possible is the same framework we still cannot name. Which brings us, Finally, to the question this whole story has been circling. We know it is there. We have known, with growing certainty, for the better part of a century. We can weigh it, map it, watch it bend light, and survive a cosmic collision and trace our own existence back to it. So what is it? What is the actual substance? After all of this, you would think the answer would be the easy part. It is not. It is the hardest part of all, and the search for it has become one of the most patient, most expensive, and most quietly frustrating hunts in the history of science. Part 8. The Suspects. Here is the honest starting point. We do not know what dark matter is, and the list of suspects is so wide that the width itself is a confession. The candidates physicists take seriously span something like 90 orders of magnitude in possible mass. That phrase is hard to feel, so let me unpack it. It means the lightest serious candidate and the heaviest serious candidate differ in mass, not by a little, not by 1,000 times, but by a 1 followed by about 90 zeros. We are not arguing over the details of a known thing. We are facing a blank so large that our guesses range from particles far lighter than anything we have ever measured, all the way up to objects as heavy as small black holes. When your suspects range that widely, you are not closing in. You are still standing at the very beginning. It is worth dwelling on how unusual that width is, because it tells you something honest about the state of the search. The candidates are not small variations on a single idea, the way you might argue over the exact mass of a particle you already understand. They are completely different kinds of thing. A WIMP would be a heavy, sluggish particle, nudging atoms one at a time. An axion would be the opposite, so light that the dark matter would behave less like a hail of bullets and more like a single enormous wave washing through everything. A primordial black hole would not be a particle at all, but a compact object, perhaps the mass of a mountain, or a moon, or a star, drifting through the halo. To be hunting, at the same moment, for a heavy particle, an ultralight near wave, and a population of black holes, and to take all three seriously, is to admit that we do not yet know what category the answer even belongs to. Imagine searching for a missing animal when your honest list of possibilities runs from something smaller than a bacterium to something larger than a whale. That is roughly where we stand. The three search strategies each carry their own quiet drama. The indirect searches stare at the crowded center of our galaxy, where dark matter is thickest, hoping to catch the faint flash that might appear if two dark matter particles happen to collide and destroy one another, reading the sky for a glow that ordinary sources cannot quite explain. The production searches, at the Great Collider near Geneva, smash ordinary particles together at almost the speed of light, and then carefully add up everything that comes flying out, watching for energy that has gone missing, carried off, perhaps, by a new invisible particle that slipped through the detectors unseen, and the direct searches wait underground, which is where we are about to go. For decades, the WIMP sat at the center of all three efforts, the favorite, the expected answer. As its territory has emptied out, year after year, the field has quietly broadened its attention toward the axion, toward lighter and stranger candidates, toward the uncomfortable possibility that the universe's most common matter is something nobody has yet thought to look for in the right way. That said, the suspects are not all equally favored, and for decades one stood out. It is called the WIMP, which stands for Weakly Interacting Massive Particle, and for a long time it was the leading candidate by far. A WIMP would be a fairly heavy particle, somewhere around the mass of an atomic nucleus, that ignores light entirely and interacts with ordinary matter only through gravity, and just barely through the weak nuclear force, the same faint force involved in certain kinds of radioactive decay. The reason the WIMP became the favorite is a coincidence elegant enough that physicists gave it a nickname. If you take a particle of roughly that mass, interacting through roughly that force, and you calculate how much of it would naturally be left over from the hot early universe, the amount comes out remarkably close to the amount of dark matter we actually measure. That near match is called the WIMP miracle, and it felt like a clue dropped by the universe, as if a particle we already had theoretical reasons to expect would conveniently turn out to be the missing mass. Whole careers and enormous experiments were built around catching one. But the WIMP is not the only suspect, and as the years passed without one turning up, the others gained attention. There is the axion, a particle at the opposite end of the scale, extraordinarily light, far lighter than anything yet detected. The axion was not invented to explain dark matter at all. It was proposed to fix a separate technical puzzle about why the strong nuclear force behaves more symmetrically than it has to. But it turned out that if axions exist, they could also fill the universe in just the right quantity to be the dark matter, and they have a tantalizing property in a strong magnetic field. An axion can occasionally convert into a particle of light, which gives experimenters a way to try to catch one. There are sterile neutrinos, a hypothetical, heavier, and even more antisocial cousin of the ordinary neutrino, particles that would ignore even the weak force. And there are primordial black holes, not the kind that form when a giant star dies, but black holes that might have formed directly out of the densest patches of the infant universe, in its first instance, and could still be drifting through the halos of galaxies today. There is even the most conservative guess of all, the one that tries to avoid new physics entirely. Maybe, the idea goes, the missing mass is just ordinary matter that happens to be dark, in the plain sense burnt-out stars, cold planets, faint failed stars too dim to see, stray black holes, all the unglamorous dim objects scattered through a galaxy's halo. These were given the name macos, partly as a joke against the WIMPs. It was a sensible thing to check, and astronomers checked it carefully by watching for the brief brightening that happens when one of these dim objects drifts in front of a more distant star and bends its light. They watched millions of stars for years, and they did not see nearly enough of these events. There are simply not enough dim, ordinary objects to be the dark matter. That conservative escape route was closed by observation. Whatever the missing mass is, the bulk of it is almost certainly not ordinary matter hiding in the dark. It is something genuinely new. So how do you catch something genuinely new? Something that barely touches ordinary matter at all? Physicists pursue three different strategies at once. The first is to try to catch a dark matter particle directly, here on Earth, by waiting for one of the rare occasions when it bumps into ordinary matter and nudges it. The second is to look outward, to the sky, hoping to spot the faint signal that might be produced if dark matter particles, in the crowded center of the galaxy, occasionally collide with one another and destroy each other, releasing a flash of ordinary energy we could detect. And the third is to try to manufacture dark matter on purpose, by slamming ordinary particles together at enormous energy in machines like the Large Hadron Collider, and watching to see if any of that energy disappears into a new, invisible particle. 3 strategies. Decades of effort. Some of the most sophisticated instruments humanity has ever built, in mines far underground, on mountaintops, in orbit, and in the largest machine ever constructed. And here is the pattern that has emerged from all of it, the pattern we will sit with for the rest of tonight. Each search has been getting better and better, more and more sensitive, ruling out more and more of the places dark matter could be hiding, and not one of them has caught it. The strange rhythm of this hunt is that the better we look, the louder the silence becomes. Every improvement narrows the hiding places without finding the prey. To feel why that silence is so hard-won and so strange, you have to go to the place where the most patient version of the hunt happens, not up toward the stars, but down beneath a mountain of solid rock into one of the quietest and most carefully shielded rooms human beings have ever made. Part 9. A Mile Underground. The idea behind catching a dark matter particle directly is almost absurdly simple, and the difficulty is almost absurdly large. It works like this. If billions of dark matter particles really are streaming through everything all the time, then once in a great while, by sheer chance, one of them should strike an atomic nucleus dead on and make it recoil the way an invisible cue ball might nudge a billiard ball just enough to see it twitch. In the right material, that tiny recoil produces a faint signal, a small flash of light, a few freed electrons. So the plan is to build a target out of a great many atoms, watch it with exquisite patience, and wait for one of those nudges. That is the whole concept. Fill a tank with something, and wait for the invisible to knock on a single atom. The catch is that the knock is unbelievably rare and unbelievably faint. We are talking about maybe a handful of these events in a year, in a tank holding many tons of material, possibly fewer. And the universe is full of other things that produce flashes that look almost identical. Cosmic rays rain down from space constantly, slamming into everything at the surface. Natural radioactivity hums quietly inside the surrounding rock, inside the steel of the tank, inside the glass of the sensors, inside the wiring, even inside our own bodies. Every one of those produces little flashes, and any one of them would swamp the whisper of a real dark matter event 1,000,000 times over. Trying to catch a dark matter particle at the surface of the Earth would be like trying to hear a single falling pin in the middle of a roaring stadium. So you do everything possible to silence the stadium. You bury the experiment far underground, beneath a mile or more of solid rock, because that much rock absorbs the cosmic rays raining from space, screening them out almost entirely. You build the detector from the most radioactively pure materials ever manufactured, metals and plastics refined until almost every trace of natural radioactivity has been removed, because the experiment has to be quieter than the materials it is made of. And at the center, you place a tank of liquid xenon, a heavy element cooled until it turns to liquid, held cold and perfectly still in the dark, ringed by sensitive detectors, waiting to catch the smallest flash. The largest of these machines have names. There is one called LZ, sitting nearly a mile below the surface in a former gold mine in South Dakota, holding about 10 tons of liquid xenon. There is another called XENONT beneath a mountain in Italy. There is a third in a mountain laboratory in China. They are, in a real sense, the cathedrals of this search, enormous, painstaking, and built around a single quiet question. Let me take you down into one of them. You step into a cage at the surface and descend, and the descent takes minutes, the rock walls sliding upward past you, the daylight shrinking to a point and then gone. A mile of stone closes over your head. When the cage stops, you walk through tunnels that were once worked for gold, and then into a clean, bright cavern that does not belong down here at all, a room of polished steel and careful wiring sealed off from the dust. At the center stands the tank. Inside it, held at a cold far below anything you have ever touched, sits the liquid xenon, still as glass, and around it hundreds of sensors stare inward, never blinking, waiting. The silence is total. A mile of rock has shut out the sky, shut out the cosmic rays, shut out almost everything, and in that silence, the sensors watch. They have been watching for years. They are waiting for a single flash, one nudge, one twitch of one atom, the faint mark of something passing through that touches ordinary matter almost never. The particles are streaming through the cavern as you stand in it, through the tank, through the rock, through you, in their billions every second. The whole machine exists to catch just one of them in the act. It may take years. It may, so far, never come. The cleverness built into these machines is worth admiring because it shows how seriously the silence is taken. The xenon tank is not just a passive bucket. When a particle does strike a xenon nucleus, the recoil makes a tiny flash of light, and it also knocks loose a few electrons, which are gently drawn upward through the liquid by an electric field and produce a second flash at the top. By timing the gap between the two flashes, and by reading which sensors lit up, the physicists can reconstruct exactly where in the tank the event happened, down to a few millimeters. That matters enormously, because the faint radioactivity that remains tends to come from the edges, from the walls and the materials. So they can ignore everything near the surface and watch only the pure xenon at the very center, the most quietly shielded volume of matter on the planet. They are not just listening for the pin to drop. They have built a room where they can tell, from the faint reflections alone, precisely which corner the sound came from, and throw away everything that came from the walls. Hundreds of scientists, across many countries, give years of their working lives to a single one of these experiments. They refine the materials, calibrate the sensors, model every stray source of background, and then they wait. There is a particular kind of patience in it that does not really exist elsewhere in science. Building an instrument of staggering sensitivity, lowering it beneath a mountain, and then sitting with it in the dark for years, fully aware that the headline result may be, once again, that nothing happened. And as you stand in that cavern in your mind, with the cold tank glinting and the sensors staring inward and the particles pouring silently through all of it, you start to feel the strange shape of the whole endeavor. We are surrounded by this stuff. We are soaked in it. And we have built the quietest, most careful rooms in human history to catch a single one of its particles in the act, and it will not knock. These are the most sensitive instruments of their kind ever built, and each new version is more sensitive than the last. The amount of care poured into them is genuinely moving when you sit with it. The refining of the materials, the shielding, the cold, the patience, all of it aimed at hearing one whisper from the most common matter in the universe. Generations of physicists have given their careers to this, building quieter and quieter rooms, larger and larger tanks, waiting in the dark for the invisible to tap once on the glass. And here is where the story turns, and where it becomes genuinely strange rather than merely difficult. After all of this, after the mile of rock, the purest materials ever made, the tons of xenon, the years of watching, the steady climb to sensitivities no one could have dreamed of a generation ago, the tanks have stayed silent. The most sensitive search ever mounted for the most abundant matter in the universe has, so far, caught nothing, not a confirmed whisper. And it is not only the underground tanks. The telescopes looking for the glow of dark matter destroying itself in the galaxy's center have found nothing they can confirm. The Large Hadron Collider, trying to manufacture it, has found nothing. 40 years of looking across 3 completely different strategies, and the prey has not appeared. What do you do with a silence like that? After 40 years, the silence stops being an absence of news and starts becoming the news itself. Part 10. 40 Years of Silence. The silence is not empty. It has been steadily eating the favorite suspect alive. Remember the WIMP, the weakly interacting massive particle, the candidate that the near-perfect coincidence of the so-called miracle made everyone's favorite. Almost every large underground experiment was built, in large part, to find it. And as those experiments grew more sensitive, year after year, they did something specific and merciless. They ruled out the WIMP's home territory. The particular masses and interaction strengths where the most natural, most theoretically beloved WIMP was supposed to live, the searchers went there, looked carefully, and found nothing. Then they pushed further into the WIMP's possible hiding places, and found nothing there either. The elegant, expected particle that should have been sitting right where the theory pointed has been pushed out of almost all the room it was supposed to occupy. It has not been formally killed everywhere it could conceivably hide, But the place it was most expected to be is now, as far as we can tell, empty. The most sensitive look yet came very recently. In December of 2025, the experiment called LZ, that 10-ton tank of liquid xenon, nearly a mile underground in South Dakota, reported the results of the largest dark matter dataset ever collected. 417 days of watching gathered between March of 2023 and April of 2025. The most sensitive search for this particle that human beings have ever performed. And the result was the same result as always, only more so. No dark matter, no confirmed nudge. The cleanest, sharpest, most patient look anyone has ever taken, and the tank stayed silent. What LZ produced instead was the best limits in the world on where the particle is not a more precise map of absence than anyone had ever drawn. It is worth understanding what those limits actually mean, because "we found nothing" can sound like failure when it is really something more specific and more relentless. Each experiment, by finding nothing, rules out a whole range of possibilities, particular combinations of how heavy the particle could be and how strongly it could interact. Every more sensitive search rules out more of those combinations, shrinking the territory where the particle could still be hiding. So the searches have not been idle. They have been steadily clearing the map, crossing off region after region where dark matter was thought most likely to live. Over the past few decades, the sensitivity of these experiments has improved by an enormous factor, generation after generation, each one peering into fainter and fainter interactions. And the prize for all that improvement has been to cross off the most promising ground and find the particle was not there either. There have been false dawns along the way, which only sharpen the ache. One experiment, running for many years under a mountain in Italy, has long reported a tantalizing yearly rhythm in its signal, rising and falling with the seasons, in exactly the way a wind of dark matter should, as the Earth swings around the Sun. For a while, it looked as though it might be the first true detection. But no other experiment has been able to reproduce it, and careful searches built specifically to check it have come up empty, leaving it an unexplained oddity rather than a discovery. Time and again, a hint has flickered, hopes have risen, and the hint has faded under scrutiny. And now the searches are running into that final wall, the neutrino fog, where the sun's own ghost particles begin to mimic the signal. We have arrived, after 40 years, at the edge of what this entire method can do, holding the most detailed map of absence ever made, and no closer to a name. But the same experiments crossed a threshold recently, that is, in its own way, the strangest and most poignant turn in the whole 40-year hunt. The detectors have become so sensitive that they have started to detect neutrinos from the sun. Neutrinos are real, known, ghostly particles, pouring out of the sun's core in unimaginable numbers, and they too, very rarely, can nudge an atomic nucleus in just the way a dark matter particle would. For decades, the detectors were not sensitive enough to notice them. Now they are. LZ and the other leading tanks have begun to see the faint signature of solar neutrinos registering in their xenon. And this is a problem, a serious and structural problem, because a neutrino nudge and a dark matter nudge can look almost identical. The neutrinos form a kind of haze, a background that cannot be shielded away, because neutrinos pass through a mile of rock as easily as they pass through a pane of glass. Physicists have given this haze a name. They call it the neutrino fog, and, as the dark matter searches push to ever greater sensitivity, they are now sinking into that fog, where the sun's own ghost particles blur the very signal they are hunting for. It is worth pausing on how strange that flaw really is. For most of the history of these experiments, neutrinos were far too faint to register, and physicists treated them as a distant, theoretical nuisance that would matter only someday. Someday has arrived. The neutrinos are now showing up as a real signal, the unmistakable touch of particles born in the nuclear fire at the center of the sun, registering in tanks that were built to catch something else entirely. There is a quiet irony in it that the people running these experiments feel keenly. The same extraordinary sensitivity that was supposed to finally reveal the dark matter has instead revealed the ghosts of our own star, and those ghosts now stand between us and the thing we are chasing, a haze that no amount of rock or shielding can ever clear away, because neutrinos pass through rock and shielding exactly the way dark matter does. To push much past this flaw, the search may need entirely new kinds of detectors that no one has yet built. Sit with the shape of that, because it is not the shape we expect from science. We tell ourselves a story about discovery, and the story goes like this: build a better instrument and you will see more. Sharpen the lens and the blur resolves into something new. For 400 years that story has mostly held. Better telescopes found more galaxies. Better microscopes found the machinery of the cell. Better detectors at the colliders found new particles, one after another. The reward for looking harder has almost always been to find something, but here, with the most abundant matter in the universe, the story has broken. We have built the most sensitive instruments in human history, refined to a degree that would have seemed impossible a generation ago, and aimed them at a substance we know with absolute certainty is streaming through them in enormous numbers every second. And the reward for all that sensitivity has been to find nothing, worse than nothing. The first thing our greatest sensitivity has revealed is not the dark matter at all, but the faint, intervening ghost of our own sun, rising like fog to make the search harder still. The better we have looked, the louder the silence has become. We are closer to the limit of what these methods can ever do, and no nearer to the answer. There is something almost vertiginous in that, if you let yourself feel it rather than just note it. The unknown is not retreating as we advance on it. In a sense, it is growing. Each null result does not shrink the mystery. It sharpens our certainty that whatever this is, it is stranger and more elusive than the comfortable guess we started with. We are not slowly cornering a familiar animal. We are learning, year by year, just how little our familiar ideas have to do with it. The most common matter in the universe has sat in the room with us the entire time, and the harder we strain to make it out, the more completely it keeps its silence. So at some point, an honest mind has to turn around and ask the question no one in this field enjoys asking out loud. What if the silence means we have been wrong from the start? What if 40 years of finding nothing is not bad luck or insufficient sensitivity, but the universe trying to tell us something? What if there is no particle to catch, because the missing mass was never a substance at all, and the thing that needs fixing is not our list of particles, but our understanding of gravity itself? Part 11. What if it isn't there? This is the most important question a skeptic can ask, and the channel owes it an honest answer rather than a dismissal. The suspicion goes like this. Physicists looked at galaxies behaving in ways their equations could not explain, and rather than admit the equations were broken, they invented an invisible substance to balance the books, a substance conveniently impossible to see, conveniently undetectable, conveniently there, in exactly the amount needed to make the sums work. Is that not a little too convenient? And history gives the suspicion real teeth. In the 1800s, astronomers noticed the orbit of Mercury behaving slightly wrong, and some of them proposed an unseen planet, which they named Vulcan, hiding close to the Sun and tugging on Mercury. They searched for it for years. Vulcan did not exist. The real answer was that Newton's theory of gravity was subtly incomplete, and only Einstein's relativity, decades later, explained Mercury without any hidden planet at all. Physics also once believed in the ether, an invisible medium thought to fill all of space so that light would have something to travel through. That did not exist either. So the move of inventing an invisible thing to rescue a theory has, more than once, been exactly the wrong move. The skeptic is standing on real ground, and there is a serious scientific alternative, not a crank idea, but a genuine theory that takes this suspicion and makes it precise. In 1983, the physicist Mordechai Milgrom proposed that we have been making a mistake not by missing matter, but by misusing gravity. His idea, called modified Newtonian dynamics, or MOND, says that at extremely low accelerations, the gentle, almost imperceptible pull found in the far outskirts of galaxies, gravity is slightly stronger than Newton's law predicts. Add one new constant of nature, a threshold acceleration below which the new behavior kicks in, and something remarkable happens. The flat rotation curves that Vera Rubin found, the curves that refuse to fall, come straight out of the math, with no dark matter required at all. The fast outer stars are explained not by invisible mass holding them, but by gravity itself behaving differently out there. I want to be fair about how well this works, because it is easy to wave MOND away, and it does not deserve that. At the scale of a single galaxy, MOND is genuinely impressive. There is a tight, almost suspiciously neat relationship between how much ordinary visible matter a galaxy contains and exactly how it rotates. Give MOND the visible matter, and it predicts the rotation with remarkable accuracy across a huge range of galaxies using its one constant. This is the same tight regularity we noticed earlier, the way a galaxy's rotation seems to know about its visible matter, locked together in a clean relationship. For dark matter, that tightness is a little awkward, because the dark matter is supposed to be free to be arranged in many ways, and yet it always seems to arrange itself in just the proportion that reproduces the pattern. For MOND, that same tightness is not awkward at all. It is the central prediction, the thing the theory was built to produce. So, at the scale of a single galaxy, MOND is not just keeping up with dark matter. In places, it is doing better, explaining with one simple rule what dark matter explains only by arranging itself carefully. Any honest account of this subject has to say that plainly. If galaxies were all we had, the modified gravity idea might well be winning, and the stakes of which answer is right could hardly be larger, because the two possibilities point at different broken pillars. If dark matter is real, then our theory of gravity is fine, and our list of the universe's ingredients is badly incomplete. There is a whole substance we have never met. If MOND is right, then our inventory of matter is fine, and our theory of gravity, the one Newton began and Einstein perfected, is incomplete in a way we have not yet grasped. One of those two pillars is cracked. The evidence, taken as a whole, leans hard toward the missing substance, because that is the only answer that survives every scale at once. But a thoughtful minority keeps the other possibility alive, and they are right to, because the regularity in the galaxies is a real clue that the simplest dark matter story does not fully explain. The most intellectually honest position may be the least comfortable one, that we do not yet know, and that the final answer might even borrow from both. Dark matter, by contrast, has to arrange itself in just the right amount in each galaxy to reproduce that same tight relationship, which is a little awkward because dark matter is supposed to be free to be distributed in many ways. So if you looked only at individual galaxies, you might well conclude that MOND is the better theory, and many thoughtful people have. But the universe is larger than single galaxies, and this is where MOND runs into walls. Go up to the scale of galaxy clusters, like Zwicky's old Coma cluster, and MOND helps, but does not solve the problem. Even with modified gravity, clusters still seem to need some additional unseen mass. The discrepancy shrinks. It does not vanish. Then there is the Bullet cluster, the cosmic collision from earlier, and this one is especially hard for MOND. In a pure modified gravity picture, the gravity must come from the visible matter, so it ought to be centered on the hot gas, where most of the ordinary matter is. Instead, the gravity sits far from the gas, out where the invisible matter sailed. A theory that says there is no dark matter has to explain why the gravity is strongest where the visible matter is not, and that is a very steep thing to explain. And then there is the oldest light, the cosmic microwave background. The pattern of those ancient ripples, the relative heights of the peaks, is explained cleanly and precisely by a substance that does not feel light, by dark matter behaving exactly as we described. Matching that pattern without real dark matter has proven extraordinarily difficult. The attempts tend to end up smuggling something dark matter-like back in. There was even a verdict from the sky in 2017 when a collision of two neutron stars sent out both light and gravitational waves, and the two arrived at Earth essentially together, showing that gravity travels at the speed of light. That single observation strained a whole class of the relativistic theories built to make MOND work, which had needed gravity to travel a little differently. So here is the honest scorecard, and it is uncomfortable for everyone. MOND describes individual galaxies beautifully, and the universe as a whole poorly. Dark matter describes the universe as a whole beautifully, clusters, lensing, the ancient light, the growth of all structure, and the centers of small galaxies, somewhat awkwardly. Each idea is strongest in exactly the place the other is weakest. A small number of researchers suspect the final answer may be some combination of the two, that we may be wrong about a little of our gravity and also missing some real substance. Most physicists weigh the whole body of evidence and conclude that the substance is real because it is the only idea that holds up across every scale at once. And that is the answer to the fudge factor charge, finally. The ether was killed by a single, clean experiment. The invented planet Vulcan was killed the moment Einstein explained Mercury without it. Both invisible fixes fell quickly because they were each a single patch on a single problem, and a single problem can be solved another way. Dark matter is not that. It has survived 40 years of the most determined attempts to kill it, and it keeps being demanded by new data it was never designed to explain. Zwicky did not know about the cosmic microwave background. Rubin was not thinking about cluster collisions. And yet the same invisible mass, in the same proportion, keeps being required by each new and independent measurement. A fudge factor explains the one thing it was invented for. Dark matter explains the entire sky, from a single spinning galaxy to the structure of the whole cosmos, with one assumption. That is the opposite of a fudge, and it is all the more maddening that we still cannot say what the thing actually is. So the suspicion, taken as seriously as it deserves, does not make the mystery go away. It sharpens it into a fork, and both paths are humbling. Either there is a substance filling the universe that we cannot find, or there is something wrong with gravity itself that we cannot pin down. There is no third option in which everything is fine. One of the two great pillars of physics is incomplete, and we do not get to know which one. We are left exactly where we began the night, but heavier now, carrying everything we have learned. We know where it is. We have no idea what it is. Part 12. The Stranger in the Room. We are about to know where dark matter is in more detail than ever before, and not one bit closer to knowing what it is. A space telescope called Euclid is, right now, mapping the invisible universe. It does this with the light-bending trick by measuring the slightly distorted shapes of millions upon millions of distant galaxies. It can reconstruct where the unseen mass that warped their light must lie. Already it has surveyed thousands of patches of sky and tens of millions of galaxies, and over the next years it will chart the distribution of dark matter across a huge fraction of the sky and across 10 billion years of cosmic history. With its first major cosmological results expected in 2026. When it is done, we will have the finest map of dark matter ever made a chart, of the scaffolding of the entire reachable universe, showing the great web of the invisible in beautiful, precise detail. And every line on that map will be drawn around a question we still cannot answer. The map will show, with extraordinary precision, where the stuff is. It will not contain a single word about what the stuff is. If anything, the better the map gets, the stranger the situation becomes, because the gap between how exactly we can locate this substance and how completely we fail to identify it will only grow wider. We are becoming the world's most precise cartographers of a country no one has ever set foot in. So let me bring this all the way home, out of the clusters and the colliders and the underground tanks, into the room where you are right now. As you lie here, in the dark, listening, the dark matter is here too. It is not a distant thing, out at the edge of the cosmos, safely far away. It is in this room. The same invisible substance that holds the galaxy together, that bent the light around the bullet cluster, that built the scaffolding the sun and the earth were assembled on it, is streaming through the walls, through the ceiling, through the bed beneath you, and through your own body in its billions, this very second, and the next, and the next. It is passing through your chest as it rises and falls. It is pouring down through the floor, through the rock, through the whole body of the earth, and out the far side into the night, almost never touching a single atom of any of it. You cannot feel it. You will never feel it. But it is here, as much a part of this room as the air, and far more a part of the universe. The greatest unsolved mystery in all of science is not waiting for you at the end of some impossible journey to the edge of space. It is here, now, moving through you while you breathe, and it always has been. There is something almost tender in the ordinariness of that. We tend to put our great mysteries far away at the edge of the universe, inside the black holes, back at the first instant of time, in places no one can ever go. This one is not far away. It is in the weave of your own room, in the space between your hands, passing through the pages of the book on the nightstand and the warmth of the blanket over you, without disturbing a single thread. It asks nothing of you. It does no harm. It simply moves through, as it has moved through every person who has ever lived, every night of human history, entirely unfelt. People fell asleep inside this invisible tide long before anyone knew it was there, and they will go on doing so long after tonight. The mystery is not cold or threatening. It is patient and quiet and close, and the work goes on, gently, in the background of all our sleeping. That space telescope is still out there, night after night, measuring the bent shapes of one galaxy after another, slowly assembling the finest map of the invisible we have ever had, with its first great results due to arrive soon. Somewhere a mile underground, the cold tanks are still watching, still waiting for the one knock that may yet come. We may meet this stranger after all one quiet night. An atom may twitch in just the right way, and a century of waiting will end in a single flash. Or the answer may arrive from a direction nobody is watching, the way the truth about Mercury's orbit came not from a hidden planet, but from a new shape for gravity itself. We do not get to know which, tonight. But people are still listening for it, with extraordinary patience, in the dark, and that, too, is a kind of beautiful. Think back to the picture we started with. The night sky as a thin froth of light riding on the surface of an ocean you cannot see. You know now what the ocean is. The foam is everything that shines, every star, every galaxy, every world, the entire bright 5%, including the atoms that make up you. And the ocean is the dark matter, the unlit majority, the thing that decided where the foam could gather, that dug the wells the galaxies formed in, that gave the universe the head start it needed to ever make anything at all. We are the foam. We are the bright, thin, beautiful exception, floating on a darkness that made us and surrounds us and runs straight through us, and that we are only beginning to understand. Far from being frightening, there is something almost gentle in it to know that the part of the universe we belong to is small and rare and luminous, and that it rests on something patient and enormous that asks nothing of us and holds everything together. Maybe one night, in one of those silent tanks a mile underground, a single atom will finally twitch in just the right way, and the long silence will break, and we will at last meet the stranger that made us. Maybe the answer will come from a direction no one is looking, the way the answer to Mercury's orbit came not from a hidden planet, but from a new shape for gravity itself. Or maybe this is one of those questions that stays open for a very long time, handed down from one generation of curious people to the next, each one mapping it a little more precisely, none of them quite able to name it. We do not get to know which tonight. What we do know is enough to sit with. There is a substance that makes up most of the matter in the universe. It is older than the first star. It built the framework that every galaxy, including ours, was assembled inside. It is, in the most literal way, the reason you are here to wonder about it. We have measured it, weighed it, watched it bend light and survive a collision between worlds, and mapped where it lies across the whole of the reachable cosmos. And after 90 years of looking, and 40 years of the most patient searching human beings have ever done, the most abundant matter in existence remains something we cannot see, cannot touch, cannot make, and cannot name. It is here in the room with you as you drift towards sleep, passing through you, holding the galaxy together, asking nothing. We know exactly where it is. We have no idea what it is. And perhaps, for tonight, that is the most honest and the most quietly astonishing thing there is to know about the universe, that the thing it is mostly made of is a stranger we have never met, and that the stranger is already here.